for it on this computer. Okay. So this is Linear Algebra Lecture 23, and I want to show two examples that are geometrically very important and very natural of linear transformations in the ordinary plane R2. The first is rotation by an angle alpha, and we always measure angles in radians. So suppose R alpha is the linear map, the function, where you take a vector v and you rotate it by alpha radians, and you get to R alpha of v. So I want to find the matrix for this linear transformation, which means we have to find out, we have to compute what rotation does to a basis. And we take the standard basis, E1 is 1, 0, and E2 is 0, 1. So if I take a unit vector on the x-axis and I rotate it by alpha radians, you learn in calculus and pre-calculus and wherever you learn about angles and trig functions, the coordinates of this vector are cosine alpha, sine alpha. If you take a unit vector in the y direction, the vector 0, 1, and you rotate it by alpha radians, the x component is minus the sine of alpha, and the y component is cosine alpha. So the matrix for a rotation by an angle alpha is this. And in fact, from this matrix, you get a lot of simple proofs of algebraic identities. For example, suppose you rotate by alpha and then you rotate by beta. That's the same as rotating by alpha plus beta. So we have the simple identity that is R alpha, R beta is R alpha plus beta, right? If you rotate, let me do it the way we usually write. If you rotate by alpha and then you rotate by beta, the net result is a rotation by alpha plus beta. And let's see what this says in terms of the matrices. So the matrix for R beta is cosine beta, sine beta, minus sine beta, cosine beta. And the matrix for alpha is cosine alpha, sine alpha, minus sine alpha, cosine alpha. What happens when you multiply these matrices? You get cosine alpha, cosine beta, minus sine alpha, sine beta. And this coordinate in the second row, first column, is cosine alpha, sine beta, minus sine alpha, cosine beta. In the first row, second column, you get minus sine alpha, cosine beta, minus cosine alpha, sine beta. And actually, this is a plus sign here, this plus this. And second column, second row, second column is cosine alpha, cosine beta, minus sine alpha, sine beta. But that's equal to R alpha plus beta. The matrix for this is the cosine of alpha plus beta minus the sine of alpha plus beta, plus the sine of alpha plus beta, minus the sine of alpha plus beta, cosine of alpha plus beta. And when you compare these two matrices, this coordinate is equal to this. That's the addition theorem for the cosine. Cosine of alpha plus beta is cosine alpha, cosine beta, plus sine alpha, minus sine alpha, sine beta. And when you compare this coordinate and this coordinate, you get the addition theorem for the sine. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So, and this is the world's easiest proof of the addition theorem for the sine and the cosine. So this is a very basic linear transformation in the plane, where you take a vector and you simply rotate it through an angle alpha. Okay, so that's a reflection. Sorry, that's a rotation. And now I want to find a matrix representation for a reflection. So a reflection means here you have the plane, you have some line through the origin. This is some line. Let's say this line makes a certain angle alpha with the x-axis. And if I take a vector v, the way we reflect the vector through the line is you draw the perpendicular to the line and you go the same distance onto the other side, and that's the reflection from here reflecting through this line. And so I'll call this S alpha of v. Okay, so that's reflection through the line. This is, so S alpha is reflection through the line, through the origin, that makes a certain angle alpha with the positive x-axis. So the angle line can go up or the line can go down, but it's a line through the origin. So how can we describe the line? Let's see. If for example, if we took a certain point x0, y0 on the line, and I can take x0, and this is the y-axis, x0 positive, then the angle alpha, the tangent of alpha is y0 over x0. So alpha can always be described as the arctangent of y0 over x0, which is the function you learned about in pre-calculus and calculus. So the simplest way to work out the coordinates or the matrix for a reflection is to use polar coordinates. So again, this is all pre-calculus, and I assume everyone understands this. If you have xy is a vector in the plane, this is x, this is y. But you also have the rectangular coordinate. These are the rectangular coordinates. If you let r be the distance from the origin to the point, and if we call this angle theta, then the polar coordinates of this vector v are r and theta. So if you take a vector, the distance to the origin is r, and the angle the vector makes with the positive x-axis is theta. So let's kind of draw a picture of what happens when you rotate a vector through the line. Here's the line determined by the angle alpha. Right? So here's my vector v, and that's v. And the polar coordinates are, this is theta, and this is r. Now, if I draw a perpendicular to the x-axis, and I go the same distance on the other side, I have two right triangles, and they're congruent because they have the same legs. This is a common side, and these two sides are the same. So this is v, and this is, I'll call S alpha of v. What happens when you reflect through this line? So this is r, so this is r. What is the angle in here? This is alpha, this is theta, so this is alpha minus theta. So this angle here is alpha minus theta. So the angle that this makes with the x-axis is alpha plus alpha minus theta. So if v has polar coordinates are theta, then S alpha of v has polar coordinates the same r, but the angle is 2 alpha minus theta. So here's S alpha of v, and this is r, and this angle is 2 alpha minus theta. So what are the rectangular coordinates of this? So we know that x is r times the cosine 2 alpha minus theta. Y is r times the sine of 2 alpha minus theta. Okay. Or let me call this x prime and y prime. Okay, so let me draw a picture, another picture, just to show what we're doing here. Here we have a line. It's the line that makes an angle alpha with the x-axis. I take a vector v and I reflect it through the line. So this vector is v, and this is S alpha of v. Let's say this has coordinates x, y, rectangular coordinates, and this has coordinates x prime, y prime. How are they related? So, so v has polar coordinates r and theta. S alpha of v has polar coordinates the same r, but this angle now is 2 alpha minus theta. So x prime, right? This is x prime, y prime. This is 2 alpha minus theta, and this is r. X prime is r times the cosine of 2 alpha minus theta. And y prime is r times the sine of 2 alpha minus theta. Because these are the formulas for writing coordinates going from polar to rectangular coordinates. And we just worked out the addition formula for the cosine. This is r times cosine of 2 alpha cosine of minus theta minus the sine of 2 alpha sine of minus theta, which is r times cosine is even. This is cosine of 2 alpha cosine theta minus sine of 2 alpha, and the sine of minus theta is plus the sine of theta. And this is r, this is cosine of 2 alpha times r cosine theta, which is x, and the sine of 2 alpha times r sine theta, which is y. So x prime has coordinates sine, cosine 2 alpha, sine 2 alpha, cosine 2 alpha x, sine 2 alpha y. R, which is sine 2 alpha minus theta, we use the addition theorem for the sine. This is the sine of 2 alpha cosine of minus theta plus r times the cosine of 2 alpha sine of minus theta. This is sine of 2 alpha r cosine theta plus cosine of 2 alpha minus r sine theta, which is minus, so minus r sine theta, which is sine 2 alpha x minus cosine 2 alpha y. So the matrix for rotation through the line alpha is cosine 2 alpha, sine 2 alpha, sine 2 alpha minus cosine 2 alpha. So this is reflection through a line. So that's really very nice. So S alpha is reflection through the line that makes an angle alpha with the positive x-axis. The matrix for this is cosine 2 alpha, sine 2 alpha, sine 2 alpha, minus cosine 2 alpha. Let's do a simple check. Here's my line. I take a vector v, I rotate it to S alpha of v. Then we rotate this back. If I rotate back, I'm back where I started. So we should have S alpha squared is the identity, right? If you reflect through the line and then you reflect back again, you're back where you started. So let's just check that this matrix identity works. What's S alpha squared? This matrix squared. So that's cosine 2 alpha, sine 2 alpha, sine 2 alpha minus cosine 2 alpha times the same thing, cosine 2 alpha, sine 2 alpha, sine 2 alpha minus cosine 2 alpha. When I multiply, what do I get? Cosine squared 2 alpha plus sine squared 2 alpha, sine 2 alpha cosine 2 alpha minus sine 2 alpha cosine 2 alpha. So what's the second column? Sine 2 alpha cosine 2 alpha minus sine 2 alpha cosine 2 alpha. In second row, second column, sine squared 2 alpha plus cosine squared 2 alpha. Cosine squared plus sine squared is 1, and this minus itself is 0. So if I take the matrix for S alpha and I square it, I get the identity matrix. So everything is consistent, and this works out the way it should work out. And in fact, if you want to check, you can prove another very nice geometrical fact. Suppose you have two lines. This is some line reflection through alpha. This is a line reflection through beta. If I take a vector v and I reflect it through this line, this is S alpha of v, and then I reflect it through a second line, so this is S beta S alpha of v, this ends up here. And if you check the matrix multiplication, you see that this is exactly a rotation through a certain angle that you can calculate. So this is just a little piece of geometry, which is very nice to know. The product of two reflections is a rotation. So that's not usually something they teach you when you're learning elementary geometry, but it's something that comes out very easily from the linear algebra approach to these geometrical actions. Okay. Any questions about that? All right, now there are two important things left for us to discuss in this semester. What we haven't talked about yet is anything like what you might call the geometry of vectors, the length of a vector, or the angle between two vectors. Now, I just talked about that in the plane, but this is in an arbitrary vector space. Right? It's not clear in n dimensions what the angle between two vectors is, or any vector space V. And the second thing is, in some sense, how to simplify a linear transformation. Let's say even in the plane, suppose you have t from R2 to R2. So if you start with some vector v, it might get mapped to some vector t of v. And this is kind of complicated, because v is changing its direction, and it's changing its length, and all sorts of things are happening. What is like the simplest case? The direction of t of v does not change. And what I mean by that is, here's my vector v, and let's suppose that t of v, maybe it just moves it's along in the same direction along the line, or along the line but going in the opposite way, t of v. But in any case, v still lies on this line. That would be a very simple action. And if this is the case, v is not zero. T of zero is always zero. In this case, t of v is just some scalar multiple lambda times v. So a vector that has this property is very nice because t doesn't change its direction. The linear transformation just either extends it either this way or this way, but it still is lying on this line. And if an equation like this occurs, we say that v is, and there's a German word that's used for this, eigenvector for t, and this scalar lambda is called an eigenvalue. So in general, in any vector space, not just in 2 dimensions, in any vector space, v has to be a non-zero vector. If t of v is just some scalar multiple of v, then v is called an eigenvector for the linear transformation t, and lambda is an eigenvalue for the linear transformation t with the eigenvector v. And what I mean by saying, if you have a lot of eigenvectors, your transformation becomes simple. Suppose t, let's say, is from a vector space V to itself. And suppose there is a basis E1 up to En for t such that every vector E sub I is an eigenvector, and t of EI is some scalar lambda I, depending on the vector EI, lambda I times EI. So you have a basis of eigenvectors. In that case, let's call this basis B. What is the matrix for T? Well, E1 goes to lambda 1 E1. So the first column is lambda 1, and that's 0. The second vector, eigenvector or basis vector E2 goes to lambda 2 E2, so that's 0, lambda 2, and then zeros. The third eigenvector, lambda E3, goes to lambda 3 E3, and so on. What you get is a diagonal matrix, which is really the simplest kind of matrix there is for a linear transformation. So, I mean, if T were like 3-dimensional and it had eigenvectors and eigenvalues, let's say the eigenvalues were 2, -5, and 7, that would be the matrix for T. So T applied to any vector x, y, z you just multiply the first coordinate by 2, the second coordinate by -5, the third coordinate by 7. That's really as simple as it gets. So one sort of goal in analyzing a linear transformation from a vector space to V to itself is to see if there is a basis just consisting of eigenvectors. Because then, with respect to that basis, your linear transformation is diagonal. So let's try to analyze this in the case of just two dimensions, R2. So suppose T is a linear transformation from R2 to R2, and suppose the matrix for T is A, B, C, D. So an eigenvector V equal XY would have the property that T of V is lambda V, or A, B, C, D applied to XY is just lambda times XY. So given this matrix, we want to look for eigenvectors. Can we find an eigenvector XY such that A, B, C, D applied to XY is just lambda times XY? If I write this in coordinates, this is AX plus BY, CX plus DY equal lambda X, lambda Y. So given the matrix A, B, C, D, I want to know if there are three numbers, X and Y and lambda, that satisfy this equation. This is the same as saying X plus AX plus BY is lambda X, CX plus DY is lambda Y. Can we solve these two equations in two unknowns? Or if I put it in sort of the standard form, this is AX plus B minus lambda Y equals 0. Sorry, that's not right. Always good to do it right. This is an X over there. So if I bring lambda X from the right side to the left side, that's A minus lambda X plus BY equals 0, and CX plus D minus lambda Y equals 0. So what we want is a non-zero. We're looking for a vector XY, which is not the zero vector. We want a non-zero solution XY of these equations. So this is two equations and two unknowns. And we know that there's the unique solution 0 if the determinant of the coefficients, if you look at the matrix of coefficients, A minus lambda C, B D minus lambda, if this determinant is non-zero, then the only solution of these equations is X equal Y equals 0. So there's a non-zero solution only if, for some lambda, this determinant is 0. So there exists an eigenvector with eigenvalue lambda if and only if this determinant equals 0. We know the determinants this times this minus this times this. So A minus lambda D minus lambda minus BC equals 0. Or if we expand this, this is just a quadratic equation, lambda squared minus A plus D lambda plus AD minus BC equals 0. So the only numbers lambda that can be eigenvalues for this linear transformation, whose matrix is A, B, C, D, are lambdas that are solutions of this quadratic equation. And a quadratic equation has at most two solutions. So there are at most two solutions lambda. If you find such a lambda, then you can solve these equations and you can get an eigenvector X and Y.
Could you show us an example?
Yes. I just want to make sure I can find an example. Let me just look for an example in the text. That's the easiest thing. And I want it to be, okay. So this is an example in the text. So this is on page 337. I have the matrix A, which is 7, 5, minus 4, 2. So this defines a linear transformation from R2 to R2, right? So if I take a vector V with coordinates x, y, T of V, that's 7, 5, minus 4, 2, that's times x, y, that's the vector 7x plus 5y minus 4x plus 2y. And I would say this is complicated. I mean, it's hard to understand geometrically or physically what this linear transformation is doing. Like, it takes the vector 1, 0 to the vector 7 minus 4. It takes the vector 0, 1 to the vector 5, 2. I mean, it's just complicated. So we can better understand this linear transformation if we're lucky enough that it has a basis of eigenvectors. So how do we compute the eigenvectors? Let me just go through it from scratch. So A of x, y is 7x plus 5y minus 4x plus 2y. That's what I just calculated. That's equal to lambda times xy, or lambda x lambda y, if x and y solve this system of linear equations. 7x plus 5y equals lambda x minus 4x plus 2y equals lambda y, which is the same as the system 7 minus lambda x plus 5y equals 0 minus 4x plus 2 minus lambda y equals 0. And in order for this system to have a non-zero solution, the determinant of the matrix of coefficients we want that to be 0. What is this determinant? It's this times this minus 5 times minus 4. That's lambda squared minus 9 lambda plus 14 plus 20. Let's see. 7 minus lambda. I'm sorry. In the example in the book, this is a minus 2. So I just want to keep it in the example in the book. Minus 2 minus 4x minus 2y. So this is a minus 2. So this is minus 2 minus lambda. So when I multiply out, I get lambda minus 2 minus lambda. I get lambda squared minus 7 lambda plus 2 lambda is minus 5 lambda, and minus 14 plus 20. So this is lambda squared plus 5 lambda plus 6. And I want that to be equal to 0. But I learned in high school that I don't have to use the quadratic formula. This is lambda plus 2 lambda plus 3 equals 0. Sorry, I keep doing this wrong. I just copied it down wrong. This is lambda squared minus 5 lambda plus 6. So this factors into lambda minus 2, lambda minus 3. So we get solutions, lambda 2 and lambda equal 3. So these are going to be eigenvalues. So I can find x and y which satisfy these equations. What are these equations? When lambda is 2, this system of equations is 5x plus 5y equals 0, minus 4x minus 4y equals 0, and the solution for that is x equal minus y, equal 1, say. And if I take lambda equal 3, these equations become 4x plus 5y equals 0, minus 4x again, this is minus 4x minus 2 minus lambda. So when lambda is 3, this is minus 5. So this is a solution of this is, for example, x equal to minus 5, y equals 4, minus 20 plus 20 equals 0. Solution of this is x equal 1, y equal minus 1. So if everything is correct, and I'll check it right now, if I have the matrix 7, 5, minus 4, minus 2, the vector E1, 1 minus 1, should be an eigenvector with eigenvalue lambda 1 equal to 2, and E2 equal to minus 5, 4 should be an eigenvector with eigenvalue lambda 2 equal 3. So let's check. If I take A applied to the vector 1 minus 1, that's 7, 5 minus 4 minus 2 times 1 minus 1. That's 7 minus 5 is 2. Minus 4 plus 2 is minus 2. This is exactly 2 times 1 minus 1. So AE1 is 2 times E1. So E1 is an eigenvector with eigenvalue 2. What about AE2? That's E2 is the vector minus 1, 4. So my matrix 7, 5 minus 4 minus 2 times minus 1, 4. This gives 7. Oops, something isn't wrong here. That's what, oh, minus 5, minus 5, 4. Just copied it down wrong. So this is minus 35 plus 20 is minus 15. This is 20 minus 8 is 12. Minus 15, 12 is 3 times minus 5, 4. That's 3 times E2. So E1 is an eigenvector with eigenvalue 2. E2 is an eigenvector with eigenvalue 3. So if T sub A is this linear transformation from R2 to R2, if I take this basis B consisting of these eigenvectors E1 and I2, the matrix for T with respect to the basis B is simply 2, 0, 0, 3. So this is the matrix with respect to this basis, which is much simpler than the matrix that we started with. And geometrically, what is happening This is 4, 8, 12 to make it easy. So if I take the vector 1 minus 1, it gets sent to the vector, that's E1, 3 times that. So this just gets sent to here. This is E1, this is 3E1. If I start with the vector minus 5, 4, that's E2, it just gets moved along this line, stretched out by a factor of 3. This is 3E2. So this is T of E2 is 3E2. T of, this is a 2. T of E1 is 2E2. So these are the basis vectors, and they just get stretched. Now, that's the geometry of this. And in wherever linear algebra is used, I mean, for example, one of the great discoveries 100 years ago in physics was quantum mechanics, where you have, let's say, hydrogen atom, you have a proton in the nucleus, and it turns out you have an electron circling the nucleus. So this is E minus, your electron. And it turns out that this electron can be, think of it this way, if you like, can be certain distances from the nucleus, but they're discrete distances, and these different energies or distances to the nucleus correspond to eigenvalues of some linear operator. So if you want to understand a hydrogen atom, you have to understand how the electron can rotate around the nucleus, and it can't take on any energy. It only takes on discrete so-called quanta of energy. And there's some linear operator that's associated with the hydrogen atom, and it has eigenvalues, and the eigenvalues determine or describe precisely what are the possible energy levels of electrons circling the nucleus. And it's just, I mean, it's really a useful, you can't understand nature without understanding eigenvectors and eigenvalues. And in every application of linear algebra, of which there are infinitely many, in economics and business, eigenvalues and eigenvectors are important. But we're only going to consider the simplest cases, and the very simplest case is a 2x2 matrix, a linear operator from R2 to R2. But exactly the same thing holds no matter what the dimension of your vector space is. It can be a 3-dimensional vector space or a 5 million dimensional vector space. And in a huge amount of what is called data analysis, people come up with matrices that are 1 million by 1 million matrices. It's a huge computational problem to figure anything out, and a lot of money is spent trying to do that, and a lot of people earn good livings doing that. But we're only going to consider the easiest cases. Let me do some more examples, because you really cannot leave a linear algebra class without having mastered the calculation of eigenvalues and eigenvectors for 2x2 matrices. I should make one other observation. Of course, it's nice if you have a basis of eigenvectors, because that leads to, when you have a linear operator, a diagonal matrix, which is the simplest matrix you want. And the idea is always in math and science to make things as simple as possible. So we have the theorem. Let me first prove it in dimension 2. Suppose we have T is a linear operator from R2 to R2. Now, there are not necessarily eigenvalues and eigenvectors. You can only happen when the quadratic equation you write down has solutions. And you know, some quadratic equations don't have solutions, right? If you have lambda squared plus 1 equals 0, if you're only working in the real numbers, this isn't possible. The square of a number is never equal to -1. So some quadratic equations over the real numbers don't have solutions. So some linear operators don't have two eigenvectors, two eigenvalues. But so suppose V1, V2 are eigenvectors. Suppose this linear operator does have two eigenvectors with eigenvalues lambda 1 and lambda 2. And you could have two eigenvectors that have the same eigenvalue, but suppose these have different eigenvalues. Then V1, V2, these two vectors are linearly independent. So if you do have two different eigenvalues for your linear operator, then we know by this theorem that they form a basis for your vector space, and your matrix will be diagonal. So let's prove this. So we have T of V1 is lambda 1 V1, and T of V2 is lambda 2 V2. Suppose some linear combination C1 V1 plus C V2 is the zero vector. We have to show C1 equals C2 equals 0. That is, the only linear combination of C1 and C2 that gives the zero vector is the trivial linear combination when both coefficients are 0. So suppose this is true. Apply T. T of C1 V2 plus C2 V2. Well, this is 0. This is T of 0. So this is going to be the zero vector. On the other hand, because T is linear, this is C1 T of V1 plus C2 T of V2. And T of V1 is lambda 1 V1, C1 lambda 1 V1 plus C2 lambda 2 V2. So we have two vector equations. We have C1 V1 plus C2 V2 equals 0. And I have this equation. Let me write it as lambda 1 C1 V1 plus lambda 2 C2 V2 equals 0. So C1 and C2 satisfy these two equations. Let me just take this first equation and multiply it by lambda 1. I get lambda 1 C1 V1 plus lambda 1 C2 V2 equals 0. I have these two equations. If I subtract, these cancel, and I get this minus this. Lambda 2 C2 V2 minus lambda 1 C2 V2 is 0. Which is lambda 2 minus lambda 1 C2 V2 is 0. But lambda 1 different from lambda 2 means lambda 2 minus lambda 1 is not 0. So I can cancel this. I get C2V2 equals 0. V2 is not a non-zero vector because it's an eigenvector. So therefore, C2 has to be 0. And if C2 is 0, C1V1 is 0, which means C1 is 0. So if V1 and V2 are eigenvectors with distinct eigenvalues, they're linearly independent. So we now have a very nice result. It doesn't tell us everything, but it tells us a lot. Let's see. Suppose we have T of xy is A, B, C, D of xy. We have this linear transformation from R2 to R2. So T has a basis of eigenvectors if what are the equations an eigenvector has to satisfy? Ax plus by equal lambda x, cx plus dy equal lambda y, which is the same as a minus lambda x plus by equals 0, cx plus d minus lambda y equals 0. So this has a solution precisely when the determinant of coefficients, which is lambda squared minus a plus d lambda plus ad minus bc equals 0, has two distinct real solutions. So whenever this quadratic equation has two distinct real solutions, in that case, we are 100% certain that we have a basis of eigenvectors for our vector space. By the way, if you have a matrix A, B, C, D, recall the determinant of A is AD minus BC. And if I take the sum of the terms on the main diagonal, A plus B, that's called the trace of A. So another way to write this equation is lambda squared minus the trace of A times lambda plus the determinant of A equals 0. If this equation has two distinct real solutions, then we're guaranteed that we have a basis of eigenvectors. Let's look at an example. Let's pick another example. Suppose that A be the matrix 1, 2, 2, 3. So A is 1, B and C are 2, D is 3. The trace of A is 1 plus 3 or 4. The determinant of A is 1 times 3 minus 2 times 2 is minus 1. So my equation, my quadratic, equation is lambda squared minus the trace of lambda plus the determinant minus 1 equals 0. How do I solve that? Well, I can't see how to factor it, so I'll just use the quadratic formula. Lambda is minus b plus or minus the square root of b squared minus 4ac over 2a. That's 4 plus or minus the square root of 20 over 2, which is 2 plus or minus the square root of 5. So I have two eigenvalues. Lambda 1 is 2 plus root 5, and lambda 2 is 2 minus root 5. So my next job is to compute eigenvectors. So let me write down the matrix again. A is 1, 2, 2, 3. And my eigenvectors, lambda 1 is 2 plus root 5. Lambda 2 is 2 minus root 5. If I did this correct, I hope I did. So let's see. So I want to find a xy, which is 1, 2, 2, 3 of xy, which is x plus 2y, 2x plus 3y. I want that to be equal to 2 root 5 x, 2 plus root 5 y. So I have the following equations to solve. X plus 2y equals 2 plus root 5 x. 2x plus 3y equals 2 plus root 5 y. This is the same as root 5x, or like minus root 5x, plus 2y equals 0. 2x plus 2 minus root 5y equals 0. So this is two equations and two unknowns. I have to solve them. So before I do that work, let me just go back. I always like to double check what I did. I have the matrix 1, 2, 2, 3. The trace is 4, and the determinant is minus 1. So I have the quadratic equation lambda squared minus 4 lambda minus 1. By the quadratic formula, lambda is minus b, which is plus 4, plus or minus the square root of b squared minus 4ac. That's minus 1 times minus 4. So you get 4 squared plus 4, that's 20, which is 4 root 5. So I factor out the 2. I cancel the 2. So 2 plus or minus root 5, that looks like it's correct. So if I multiply the first equation by 2, and I multiply the second equation by root 5, and I add, I get 2 root 5 minus 1. Oops, something is not right. X plus 2 root 5, 2x plus 3y. This should be the eigenvector. So I get 2y equals square root of 5x. And for my second equation, I get 2x equals minus 1 plus root 5y. So something isn't right. I have a matrix 1, 2, 2, 3. And I need to solve the quadratic equation, lambda squared minus 4 lambda plus minus 1 equals 0. So the eigenvalues are 4 plus or minus the square root of 20. 20 is 4 times 5. So I get 4 plus or minus 2 root 5 over 2, or 2 plus or minus root 5. So 2 plus root 5 and 2 minus root 5 should be the eigenvalues. So I should be able to solve my equations for x and y. So 2 minus lambda 1 is minus root 5x plus 2y equals 0. And my second equation should be the same equation. 2x plus 2 minus 2 plus root 5 is minus root 5. Oh. Okay. So d minus lambda is 3 minus 2 plus root 5. That's 1 minus root 5. Let me just work this out. Let me just do this more carefully. 1, 2, 3, 4 times xy is supposed to be, this will be x plus 2y, 2x plus 3y. That's 2 plus root 5x, 2 plus root 5y. So this says that one plus root 5x equals 2y. And this says that 2x equals minus 1 plus root 5x. So that should be okay. I have 1 plus root 5x equal 2y. I take the second equation and I multiply it by 1 plus root 5x. This is equal to minus 1. This is equal to 5. This is equal to 4y, which means that 1 plus root 5x equal 2y. Good. So if I let x equal to 2 and y equal 1 plus root 5, that should be an eigenvector. So let's just double check. So if I take lambda 1 be equal to the eigenvalue 2 plus root 5, and I take E1 to be the vector x equal to 2, y equal 1 plus root 5. I hope it is the case that AE1 is lambda 1 E1. That's the equation for an eigenvector and an eigenvalue. So let's check. So AE1 is 1, 2, 2, 3 times the vector 2, 1 plus root 5. That's equal to 2 plus 2 root 5. 4 plus 3 plus 3 root 5. So this is 2 plus 2 root 5, 7 plus 3 root 5. That's AE1. And what is lambda 1 E1? So lambda 1 is 2 plus root 5 times the vector 2, 1 plus root 5. So 2 times this is, oops, still not right. It's close, but no cigar. This is 4 plus 2 root 5. And when I multiply this together, I get 2 plus 5 is 7 plus 3 root 5. This is 2. This is right, but what? Something is wrong with that. This is 2 plus 2 plus 2 root 5. That's 4 plus 2 root 5. And now it is correct. Okay. So good, I win. So this is one eigenvalue, 2 plus root 5, and this is a corresponding eigenvector. And okay. All right, well, this is what I'm going to talk about after the exam next week. We have just this little bit about eigenvectors and eigenvalues, and I'm just going to be doing it for 2x2 matrices, linear operators on R2. And I also want to be able to, in general, in a vector space, define the length of a vector, the angle between two vectors, when vectors are perpendicular or parallel, the elementary geometry of vectors. And that requires what is called an inner product on the vector space. So I'll talk about that also in the couple of classes that we have after the exam on Wednesday and before the final. Okay. And again, I remind you, I have help sessions, problem sessions almost every day, but for us in particular, today at 7 p.m. and Tuesday at 7 p.m. So I encourage you to log on to this Zoom site and ask questions. Yeah. Anything before we quit for the morning or the early afternoon? If not, then we are done. Be well, everyone. See you Wednesday. Bye.